The whole point of this video is that it's accessible for everyone. Anyone from year 9 to year 13 should be able to at least learn something about one topic described in this video. Kia ora, I'm Aidan, new on the block to study time, here to talk about gradients. You may have heard the word gradient, rate of change, or relationship thrown around in maths a lot. It's an important idea as it helps us understand how things change in our world. That change is always related to what we call variables, let's say x and y. Gradients appear all over mathematics, but mainly in graphing, and then at a higher level in calculus, which starts appearing in year 12. I'll do my best to demystify calculus and explain why it isn't as scary as a lot of people think. This video is going to start by looking at the gradients of straight lines, so starting from the very start. We'll then move on to looking at calculus, and once we've got a good grasp of that, we'll move on to what happens when you start putting a function within another, called the chain rule. So first, let's think about a graph. So a graph is just a visual representation of two variables. Let's say x on maybe the horizontal axis and y on the vertical. That's conventional. And it describes the set of points, which are pairs of x and y coordinates, that exist on this graph. So if I were to make a point here, then this might be, say, 1 in the x-axis and 2 in the y-axis. And that would be what a point is. Now, if we think about a line, what that really is just a collection of points that relate x to y. So I could draw that on the graph. Maybe it looks like this. I could extend it down this way, up here. And that really is just a collection of points that map, say, x to y. So if this is the x-axis, this is the y-axis, we have a point maybe that's 3 along and 5 up. Cool. And so at its most basic, that is going to be a line that is just straight. That says that the relation between y and x is nothing, really. As x changes, y doesn't change at all. And we say here that the gradient or slope is 0. So in that case, we'd say, well, m, which denotes gradient, equals 0. Now, if we have another example, we might have a relationship because the line has some slope. So here's an example of a slope line. We know that it's not flat because as x changes, as we go further across here, from here to say here, we actually go up. We go up the y-axis by this much. Now we're starting to get into ideas of how big a gradient is. If there's a given change in x, how big is that change in y? Well, that depends on the steepness of the graph. So if I rub this graph out, maybe in red this time, well, we could have a much steeper graph. Maybe that runs up like that. And so as we get a given change in x, the same change, there's going to be a much bigger change in y, which would suggest that the gradient is a lot larger and the slope is a lot steeper. So that's important to us as we want to know how x and y are related specifically. So if it's so useful to find the gradient of the line, how do we exactly do it? Well, we take 2 points on that line, let's say here and here, and I'll just label those points. Let's say 1, 2, and 2, 4. Now, this isn't entirely accurate. We're just doing examples for now, but if we're thinking about finding the gradient, we want to find what's called the rise, which is by how much we go up, and the run as well, which is how much we go this way. If we want to find the gradient exactly, we want to divide those two numbers. So what we're going to do is we're going to look at what is the rise here. So rise, that's just going to be the difference in the two y values. So we've got a y value of 4 first, so that is, if I get a highlighter right here, and the other y value is 2. And because 4 comes after 2, we do it first, so we go like that. 4 minus 2, of course, is 2. Now we have the run. It's going from, well, 1 to 2. 2 minus 1, we say, is the difference. Is 1. So we run along 1 and we go up 2. And now, in order to get the gradient, we do rise over run. So gradient we denote with m, so we just say that m equals the rise 2 over the run 1, which just equals 2. So we now know that the gradient of that specific line is 2. Okay. All right, so now I've got another example here set up. I want you to have a go at home. Just pause the video if you're not so familiar with this topic and just try and work out the gradient of this line. It's not too complicated. It's using the exact same method as before, but it's probably going to come out as something that's a bit less than the gradient from before because we're less steep at this point. So pause the video, have a go at it, and we'll come back. Okay, we're back, and we're just going to show you the answer to this. So if I were to, like this, find the gradient here, we would be looking at the rise. The rise is what's going to be m equals the rise of the run. So we're going to have 3 minus 1 over 9 minus 3. Because the run goes from 3 to 9, and the rise goes from 1 to 3 in our y values. So that is just 2 over 6, which if we were to simplify in a calculator potentially, that's just 1 over 3. Okay, cool. That's us with gradients. Now we have to head to a bit more of a scary topic, calculus. So calculus is a scary word, it just means calculating. And what we're calculating at an NCEA level 2 level is gradients, in particular gradients at a really small point or a single point rather than for the whole line or a section of it. You may hear gradients in calculus be called rates of change or the keyword derivative. And derivatives are written like this specifically, dy by dx. We'll get to why that is later. So differentiating means finding the gradient. You can think of it as short for finding the difference in one variable when we change another. So dy by dx basically means, well, the difference in y divided by the difference in x. And differentiating is really easy at the level of a straight line because if I were to draw one of those up, we said this was, say, y equals 2x plus 5, with m, that being in the form y equals mx plus c. Then we just take the gradient when we're differentiating. So we would say that dy by dx equals the gradient, which is 2, right? Or the m part of the y equation. So as you can see, if calculus is that simple in that context, well, it's more useful for more complex equations. And at this point, we would start calling these equations functions. And functions are denoted like this. We say f of x. The derivative of a function, it's denoted like this. Denoted, not donated. F prime of x or f dash of x. It's just another way that NCEA confuses us. This is equivalent to y, and this here is equivalent to dy by dx. So what dy by dx is to y, f dash of x is to f of x. Now, if I were to give you a squiggly line, a more complicated function, we would say, this way is still x, this is still y, and I'll draw it in red for you. Now, this is a function. I wouldn't know what its equation is, but now it's no longer straight. We know that the gradient is changing as we move across the x-axis. So if I were to draw what's called a tangent line, which describes the gradient, well, that slope of that tangent line is different there to what it is right here. We can see that unlike that straight line, the gradient of this curvy line is changing. And we're concerned with what it is at each point. That's what calculus gives us. So with calculus, you can imagine that we're calculating gradients, but we're not doing it with 2 points like we were doing before. Because if we did that, well, let's just erase some of this work from before. Now, if we were doing that, well, I could pick 2 arbitrary points. I could pick any points like we would do while we're doing a straight line, and I would draw the line between them, the straight line between them, like is calculated when we're calculating the sort of rise over run with the difference between 2 points. And, you know, maybe look at this triangle here, the rise and the run. Well, that wouldn't actually be computing the gradient at a single point. It'd be computing it for the average of this entire section right here. And that wouldn't be very helpful to us because we want to be more precise when we're thinking about more complex functions. So basically, calculus is looking at that and getting these 2 points to be infinitely close together, such that there's effectively no difference in, such that there's no inaccuracy in the calculation of that gradient. So let's say that we have a graph y equals x squared. This is just in the first quadrant of the xy plane. If we want to do calculus on this, well, not do calculus, but rather find the gradient for any point, then we're going to have to shift the power over in front of the x and minus the whole power by 1. So let's say I'm doing dy by dx of this. I'm going to shift that power to the front, so it goes 2 goes to the front, so we get 2x, and then we minus 1 off the power, so we get 2x to the power of 1, which is just 2x. So now we know that at any point on this equation, we can just put in the x value, and we know that the gradient has a value of 2 times that. So at 2, for example, we know that dy by dx evaluated at x equals 2 just equals 2 times 2, which equals 4. So if I were to put a tangent line, or find the gradient of that point right here, then I know that the gradient of that tangent, it just touches right there. I know that the gradient of that tangent is exactly 4. And that's really helpful to us if we're applying that to real world situations, or we're in an exam and we need to know something. So that's the basis of calculus. And I won't go through all of how to differentiate stuff. That would be a bit of a waste of your time on this video. There's a lot of resources out there. Check out store.studytime.co.nz for that as well. But that is the basis of gradients in calculus. So now we're going to quickly head on to something that's a little more complicated, called the chain rule. So the basic bit of chain rule is this rule that says that dy by dx, right, the derivative of a function, or the gradient, equals the gradient of y with respect to u times the gradient of u with respect to x. So it's like chained together. That's the idea behind the name. So we introduce this new variable u, which looks kind of scary, right? But really, it is just another sort of way to express the inside function of a given function. So if I were to say that we had sine of 4x minus 4, well, the outside function is just sine, and the inside function is going to be this bit. So we'd say that u equals 4x minus 4. And in an exam would probably say let u, just to use mathematical language for you. So all we're doing is introducing a new variable to be graphed with these other ones and trying to examine the gradients that occur when we do that graphing. So let's have a look at an example of that. 2x minus 1 maybe to the power of 3, right? So the outside function here is, we can call the inside function u, right? We'll say u equals 2x minus 1. And this equals u to the power of 3. So the outside function is just something to the power of 3. And the inside function, well, that's 2x minus 1. And if we were to have other examples, well, we might have e to the 3c, for example. And in that case, we could say, well, let u equals 3c. So we've got e to the u is our outside function, right? And 3c is our inside function. So chain rule is just concerned with when we have a function within another. So now we come to thinking about differentiation, or finding the gradient, finding the derivative, when we've got a function within another. And that, of course, is done by chain rule. Let's say I were to graph 2x minus 1, all of that cubed. Now the trouble there is that, well, you've got one function we know how to differentiate. We've got u cubed. And we've also got another we know how to differentiate, which is 2x minus 1. So let's just graph 2x minus 1. So let's just call that x. And we'll say that this axis is u. Just try to bear with me. It's similar to y, but it's just another letter we're going to use. So 2x minus 1, well, if I were to go down a bit, then our intercept is clearly there. Go up like this. I'll use red. We could describe this line as u equals 2x minus 1. Now, we can graph as well this idea, well, let's say this is y. We can also graph y and u, because they're related, right? So we'll say y and u is on the bottom axis this time. Y is just equal to u cubed. So if we look at that, that's going to be, or at 1 we're going to get 1, and then at 2 we're going to get 8. So it's going to kind of come out like this. So this is y equals u cubed, and it just goes up and up. So what we need to think about is how as x changes, u changes, and then as u changes, y changes. So what our concern is the relationship between y and x. So how do we go from this inside function, or this x changing u, and then u changing y, to get to something where we can describe how x changes y? Well, that is not too hard when we think about how we could just graph, well, this function overall right here, but it is a bit more difficult when we consider finding the gradient. So I'm just going to go ahead and graph 2x minus 1 to the power of 3. And so now we need to find a gradient, and we can't just differentiate so easily because we need to consider the gradients of actually both functions when we're differentiating. So if we were to differentiate this, we get, well, dy by, we say du this time, equals 3u squared. Okay, and we also know that u equals something to do with x, so we'll add that in later. But here, we need to consider this derivative. Well, we know that we just take this number, this gradient, when we're differentiating. So we go du by dx equals 2. So how do we kind of compose these together to get the gradient when we're thinking about this big function with lots of stuff in it? This function that has, a function within itself, 2x minus 1. So we've got this inside function, we've called that u, and our rule is going to be the chain rule, which is just dy by dx equals dy by du times du by dx. That sounds complicated, but it's actually not too hard, because we've already found dy by du, which we know is 3u squared, but we're going to rewrite that firstly. So we know that u equals 2x minus 1. So we're just going to say that this is 3 times 2x minus 1 to the power of 2. Okay. So this is going to equal 3 times 2x minus 1 to the power of 2 times by du by dx. Now du by dx is 2. We already looked at that. Okay. So now we just multiply by 2. And we get 6 times 2x minus 1 squared. Okay, and that's pretty easy, right? So that's our derivative already, and we could sub in any point on the x-axis to find the gradient at that point on the line. This is a bit complicated. It's a bit annoying to find each derivative for each graph and draw them all out. So I'm just going to give you a more simple rule to apply here. So if I were to have a different function, let's say 3x plus 2 to the power of 5, without graphing it, we can actually consider what the derivative of it is going to be. So let's say this is y. We're going to say dy by dx, the difference in y divided by the difference in x at every point, is going to be the derivative of this sort of base function, which is, we'll say, bring the power down, multiply by the actual thing itself to the power of 5 minus 1, which is 4. And now we're going to do this sort of chain rule part, which is just multiplying by the derivative of the inside function. And let's look at that inside function. That is right here. We can see that the inside function is here. We can see that the derivative of this is just 3. It's not too hard. Just 3 right here. Now that we know that derivative, all we have to do is multiply by that. And that's going to keep your calculus teacher very happy. So the thing you have to remember to do in an exam, whenever you spot that there's a function within another, you have to multiply by the derivative of that. So if I go down and I do another type of function, let's say sine of, let's do a very simple inside function, just 4x, right? No +1 or anything like that. If I were to say that that's what, or even more trickier, f of x equals, right? What is f dash of x? Well, I know that the derivative, just from my own knowledge, if I take the derivative of sine, then I'm going to get d of sine x, because this is just y. It's basically like saying dy by dx equals cosine x. So we know that. So the derivative of sine of 4x is going to be cosine of 4x, but we're not quite considering the chain rule, because there's an inside function here, right? There's an inside function of 4x. So what we're going to have to do is we'll just take that cosine of 4x that we just remembered. This thing is on your formula sheet, by the way. And we have to multiply that by the derivative of the inside function. And that's just going to be, well, the derivative of 4x. 4x, it's basically just a straight line with a gradient of 4, so we know that the derivative is going to be 4. So like that. And we can rewrite that as 4 cosine of 4x. And that rule comes up a lot. We could see it with e to the x. If I were to have y equals e to the 3x, say, then dy by dx equals, well, let's just remember that the derivative of e to the x with respect to x is itself just e to the x. That's a formula sheet thing, I think. We need to consider, well, it's just e to the 3x times the derivative of the inside function, which is just 3. So that's going to be 3e to the 3x. Okay, cool. All right, so now let's see what we've learned. Overall gradients describe the relationship between two variables. If we go beyond just a straight line graph, calculus can help us find the gradient at a specific point. If we want to model, say, global average temperature, we can use calculus to derive a formula and then understand where we're at in said formula to see where we're headed in the future. If the global average temperature is dependent on time and the gradient is quite steep, we know it's going up fast and we're in trouble in terms of climate change. Using calculus, we can still find the gradient even if the line isn't straight. Now, using the chain rule, if we have an inside function, maybe a function for the number of cars on the road, and that is something global average temperature depends on, and then the number of cars on the road also depends on, say, time, we can still calculate the gradient of global average temperature with respect to time. I hope that makes sense, and I hope that's a good explainer of how something that you learn in, say, year 9 and 10, maybe expand on a bit in year 11, which is gradients, applies to calculus, and then eventually a sort of year 13 concept of chain rule. Thanks so much for watching, and if you want to see more resources, there's a lot of content that we have on our website for tables, equations, and graphs, and the level 2 calculus standard, as well as all level 3 calculus standards at store.studytime.co.nz or our visual guides at studytime.co.nz.